So it is a great pleasure to be back in Bonn. And so today I will speak about sphere packing, cyclotomic fields, and subconvexity bounds. And so maybe some of you know I have a thing for sphere packing, it's a bit of obsession. So I will start with this topic. And so I was asked to make this talk introductory, but I also see many mathematicians in the room. So I will try to balance and make it interesting for everyone, so everyone can take out something of the lecture. And so the way to do it, I decided to add many pictures. So, okay, so this is the first picture. It tells us about that we have our standard Euclidean space. So this is the space where our story happens. And of course, in Euclidean space, what is important, we have our favorite Euclidean distance, which means that we can speak about sphere packings. But today we will not speak about any sphere packings, but we will speak about lattice sphere packings. So sphere packings which come from lattices. And so if you are a mathematician, you already know what a lattice is. Mathematically speaking, I don't need to recall you, and it's not the same what physicists think it is. So, and for those who maybe does not know this, so maybe I can give you an intuitive picture. So here we see our two-dimensional space, which we still can visualize. And so we take two vectors through this red arrows. And now with help of them, we span a lattice. And the lattice, it would be this set of this all blue dots. So this is this very regular set of points. And so now, if we have a lattice, we can associate a sphere packing to it. So what we want to do, we want to take this blue points as our centers of the spheres, or rather balls, and we take our balls as big as possible so that they don't intersect each other, so that this is indeed a packing. And so what do we do for this? We search for the shortest vector in the lattice. And so in our lattice, we have these two green vectors are the shortest vectors. And so now if I want to put a ball, or in this case a disk with a center at each blue point, so my best chance is to take the shortest vector divided by 2, and this would be my radius of my balls. So this is how the picture of a packing would look like. And so now somehow the two-dimensional problem is not that interesting, especially for lattice packings. It's a very easy solution. So we want to go to big dimensions, and in each dimension, we would like to find the best lattice, which gives us the best packing, so the densest packing. So here, for example, we can scale our lattices so that we have 1 point per unit of volume on average, and then the game would be to find the lattice which allows us for biggest balls to be put in such an arrangement. And so first question we can ask, one thing we can do, we can ask this in different dimensions. And in dimension 2, it is easy. In dimension 3, it is maybe a bit more interesting, but also was solved classically a long time ago. And then we see that, this is the list of all the dimensions that we know. So we know the solution dimensions 1, 2, 3, 4, 5, 6, 7, 8, and 24. And so up to 8, this is actually a very old list. I think it's maybe even from 19th century or very beginning of 20th century. So very classical result. Result 24 was quite recent, so it was maybe 10, 15 years ago, result by Henry Kohn and Abhinav Kumar. And so here we see that some numbers, I put them in just regular letters, and some of them are bold. And those which are bold, it's where we know the solution not only to lattice packing problem, but to the complete packing problem. And so here you see that somehow, even though for 8 the result is very classical and very old, 9 seems to be like a very difficult question for lattices, even though we know that this is finite amount of computation, but this amount grows so fast that it's still a tough computational problem. And somehow dimension 24 is special. That's why here there is a shortcut, how 24 can be solved before then 9. And so so this is with finite dimensions, which is an interesting story on its own. What kind of methods can we do to prove this optimality? But today I would like to speak about a different story, about what What if we go to the very, very big dimension? And so as we go to the very, very big dimension, there are essentially two questions we can ask, like in any optimization problem. One of them is provide us solutions of how to get those good packings. And another one, of course, how to know that better cannot be done, how to obtain upper bounds. And my story today is about these good examples, about how to construct it, or at least how to prove that they exist. And so here the situation is the following. So this is the brief history of asymptotic lower bounds for the sphere packing constant, but also the lattice sphere packing constant. And so somehow, as we can do in many optimization problems, there are somehow two methods which usually work quite well. So if you want to solve an optimization problem, the one thing we can try a random solution and to see how good it is. And so there is another similar method. Instead of being random, we can be greedy. We can come up with an algorithm which constructs for us kind of a greedy solution. And in many optimization problems that we know, this is actually almost as good as we can do. And so this is the case for the sphere packing problem. So we can consider random configurations, or we can come up with a rather simple greedy algorithm how to do it. And if we do this, so we see that in dimension D, we can construct, we can prove the existence of a sphere packing of density, roughly speaking, 2 to the minus D, with some improvements. And so the history of improvements you can see here. So the theorem of Minkowski and Klavka, it essentially uses this idea of random lattices and various methods how to see what kind of sphere packings they give. And then there is a long story of improvements on this. And so here I just put only two, so to say, maybe important points. One of them is that somehow the exponent to the minus d at the moment, it seems unbeatable, and maybe not many people have ideas how to move forward. At the same time, it was possible to obtain this linear improvement, linear in dimension, and so this was done in the middle of the previous century. And then more recently, Akshay Venkatesh, he used the number theoretic tools, and to this linear term of improvement, he also added this small log d term. And so this is the construction I will speak about later. This is what uses ideas from number theory and extra symmetries that can be brought to the problem. And then this is a very recent breakthrough, which happened like 1-2 years ago. It's that a group of young combinatorists, what they were able to do, they were able to add, so to replace this log d improvement by log d improvement. And so here an important thing is that their theorem, it's not for lattice packings, it's for, so the packing which they guarantee the existence for does not need to be a lattice packing. It can be a more general one. And somehow the ideas that they use, they're very combinatorial ideas. They come from graph theory. So they somehow imply this powerful, recently developed methods in combinatorics to the sphere packing problem and obtain this log d term, which many people think that maybe this is somehow the end of what we can reach, or maybe even this is the right answer, who knows. And so here the idea is that so this, if we come somehow like, they take again random packing, but then compute its like average density in a more delicate way, not in the most naive way. So then we can get this log d term, and maybe in big dimensions, very big lattices, or in very big packings, they cannot be much better than random ones. But of course, it's somehow to which team you belong. It's maybe hard to. At this point, it seems more of a philosophical question. And so, so what I would like maybe to dive more into this random constructions, and maybe start with the construction of Minkowski. So how the proof of Minkowski theorem works. So this is also something very classical and very old. So, and maybe and actually, in fact, Minkowski and Klavka, they did things in a different way. at their time. So what I present here, it's maybe a bit more modern view on this question. So first of all, we need to construct this space of random lattices, because I tell you what the random lattice is, but then as mathematicians, we actually would like to have a space, and we would like to have a probability measure on it, and then we truly believe that we do have a random space. And for lattices, there is a very natural way of doing it, because we have this big algebraic group, SLDR, the group that acts on the space of lattices. And so actually we can think of a space of lattices as this quotient of the group SLDR by its a discrete subgroup SLDZ. And so we can think of this SLDR as a group which spits us a basis for our lattice, and SLDZ, it takes care of the fact that one lattice can be spanned by actually many different bases. So the action of SLDZ, it tells us, okay, but we can make it integral change of basis in our lattice, and the lattice will stay the same. And so this gives us the space we would like to study. And so on this space, we have a Haar measure, and it turns out that if we take the quotient, then this Haar measure becomes finite, so it can be normalized so that it is a probability measure. And so this way, we can speak about random lattices. And so now, if we have a random lattice, we can also maybe, if we're estimating directly like we can introduce many random variables, of course. One of them would be the length of the shortest vector. But computing this quantity, it's a bit difficult. So what turns out to be easier, much nicer quantity, which is easier to study, is to take our random lattice, intersect it with a ball, and count the number of lattice points inside of this ball. And so, of course, if our packing our lattice gives us a good packing, and our smallest ball is small enough, then the number would be 1. It will contain only 0. So this somehow controls the property we care about, even though not to the best somehow. Not very carefully. And so now what is also important is that for this random variable, we can compute its expected value. And so if here now I will show you the answer. So the usual way to compute the expected value is to use Siegel's mean value theorem. And so this theorem, it tells us the following thing. So if we have any nice functional Euclidean space, so it should be smooth enough and have fast enough decay. And so we can study not only the number of points in a ball, but for example, we can study the lattice sum of this function for different lattices. And so we might be interested in computing the average of the sum lattices over all lattices with our probability measure. And so what the answer would be, the answer is very natural thing. So what we will get as our expected value would be just the integral of our function over the whole space. And we can see this is actually a very reasonable answer, because if we take, for example, our lattices of covolume 1, then these lattice sums, they all approximate the integral of our function over the space. And so it turns out that when we take all lattices, then all the noisy part just cancels out, and we are just left with this very intuitive term. And so now we can apply this theorem to the indicator function of a ball, and this way we will get the expected value of the number of points in the ball. And so as we do this, now it's already it's an easy way to prove the Minkowski-Hlavka theorem. So it's maybe 2 lines. Okay, so we choose a ball small enough such that its volume is, for example, smaller than 2. Then we will have that the average number of points in a ball would be smaller than 2, and it means that there should be at least 1 lattice, so that the number of points in a ball, somehow not counting the 0, would be smaller than 2, and that means that the number is actually 0, because every lattice vector comes with its opposite. And so this proves for us the Minkowski-Hlavka theorem. And so, but what can we do other than random? And so, of course, there are many things we can do. Probably there should be some interesting ideas coming from combinatorics as well, but then I'll apply it also to lattices. But as I am a number theorist, I would like to present to you some ideas which come from number theory. And here's, again, it's actually a very classical topic, which also goes back to Minkowski, the geometry of numbers. And so here the idea is the following. So if we have a number field, then from the number field, we can produce naturally an Euclidean space. And if we take the integer, ring of integers in our number field, it will become a lattice in this Euclidean space. And so what we can do, we can study these lattices. And actually this was interesting not only for mathematicians, but this kind of constructions, they're used a lot everywhere where people need explicit constructions, like in coding theory or in cryptography, because it's very nice to speak about random lattices, and it's not so nice working with them. Sometimes it's nice to have something you can create, what you can actually compute and work with it. So, yeah, but then, of course, when we do this construction, there are many questions one can ask. For example, how the lattices we can get by this method, how are they compared to random ones? Where will they live in this random space? Will they equidistribute over it? Will they accumulate near some boring points like cusps that are useless for us? Will they maybe accumulate again near some extremely good and wonderful lattices? For example, many famous lattices like E8 lattice, Leech lattice, they can be constructed somehow in, maybe not in this way, but in algebraic ways. So maybe algebraic ways give actually good objects, better than average. Okay, so here's the picture I promised. So maybe it was so the previous slide was for those who are mathematicians and number theorists. Maybe this slide is for those who did not take their course of algebraic number theory recently. And so here's an example. So okay, so first, this is how so again, maybe small piece for mathematicians, this is actually how our scalar product is actually defined. It is defined by the trace norm of numbers. So like in here also, we normalize everything so that our ring of integers becomes a lattice of covolume 1. And so this is how it works. So here, like maybe a bit of explanation to all idea. If we take our simplest number field, which is Q, so we know that rational numbers, they live inside real numbers. So this is a real line, and here there are it's densely covered by rational numbers, and the integers for rationals, they're our usual favorite integers, and of course integers are the same. They cover our line in this very regular manner, so they are a lattice. It is a one-dimensional lattice, again, the simplest possible lattice. And now if we take another number field, and so here I took a totally real number field, Q adjoint square root of 5. And so, yeah, so this is totally real number field. It has two embeddings into real space. And again, if we look at at all points of this field, they will be dense in the line. But then another thing is that if you take all integer points, so integer points, they are given in this way. So what will happen then each of two embeddings will also densely embed this into our real line, and this is not what we want because we wanted to have a lattice. And so here is somehow the idea of probably Minkowski is to somehow consider these two embeddings simultaneously, and then our integral points, which were just dense on the real line, they become a very nice two-dimensional object, very geometric one. And so here, this is how this lattice looks like. So here and the connection between two embeddings is of course changing square root of 5 to the minus square root of 5. And yes, so now. But the ring of integers, it is only one lattice, and also somehow we know that for its packing properties, it's not very good because it does have many short vectors that are too short. For example, 1, so the unit of this field will be inconveniently short vectors. So we would like to have more and probably still add a bit of randomness to our story. And okay, so maybe one important thing that I did not tell is that what will become later important for the story is that also this lattice, it has a special symmetries. So if we take actually any any point here, consider its two real embeddings, and then we multiply first coordinate by the first embedding of a number here, and second coordinate by second embedding of a number, then this will create a symmetry of our lattice. So our lattice will have these nice symmetries, and so this would become important later. And so there are several things we can do with lattices. For example, we can consider lattices of higher rank, so we choose integer t, and we consider such a quotient of these two groups. So here is the, again, SLT of the area of the Minkowski space, the Minkowski space of our number field. And so, like in simple terms, it will look like this. And then we quotient it by its discrete subgroup. So we will get a space of finite volume. And so this will represent for us lattices, but now lattices with the structure inherited from the number field. And now like this new space we have constructed, it will live inside of one of our previous spaces of just all possible lattices. And there are actually even more things we can do. So if our field might have class number bigger than 1, and in that case, we can consider not only the OK, but also other integral ideals and build lattices from them. And so what is important is that for this newly constructed space, if our T, the rank is bigger or equal than 2, then the analog of Siegel's mass formula works. It's called the Siegel-Weil formula. And we also get the same, the expected value of the lattice points inside of the lattice is again the volume of the ball. And somehow what has changed now is now that we have all the symmetries. And so it means that it could happen that our number field was such that it had units, it could also not only infinite, but also finite units. And so there will be, then these finite units, their action on the Minkowski space, it will be an orthogonal action. It will preserve the scalar product. And so it means that all the intersection of our lattice with a ball, before the lattice points in a ball, they all came in pairs. So the vector and its -1. But now they will come in these bunches, which are the orbits of this finite group of subgroup of the finite units. And so this gives us a little bit of an edge, and this allowed Venkatesh to get this extra term. And so maybe one important thing I should say, that this is true not for all D, not for all dimensions D, but only for a subset of dimensions. So when I prepared slide, this information disappeared. So this works not for all dimensions D, but for special dimensions. And so the story I would like to speak about today is what happens when the rank of our lattice is only 1. So because this method, it works when T is bigger or equal than 2. But then if T equals 1, we still have some lattices. I will show to you in a moment how to have more than just one lattice, which is the embedding of the ring of integers. So what happens if T equals 1? Okay, so at first let me tell you if T equals 1. So maybe this is a slide from mathematicians on how to construct a bit more bigger set of lattices. And so if T equals 1, what is a natural thing to consider would be the Arakelov class group. And so it works the following way. So we take our ring of integers, we look at its ideal class, we take fractional ideals in different ideal classes, and we consider the pairs. And our pair would be some ideal and an element of this group of the, it would be a set of all elements of the Minkowski space where their norm, which is a product of coordinates, is equal to 1. And if somehow, if the embeddings are real, we take norms of real numbers. If embedding is complex, then we take the product of the norms of complex numbers. So then we still somehow inside of this group here, we still have our group of integers. So we have to take a quotient because the multiplication by the group of integers, it actually somehow leaves our ideal, does not change our ideals. And so we will consider a short exact sequence like this. And it's also an important fact, it's what we know from a Dirichlet unit theorem. We know that this quotient, it's a compact torus. So we have now constructed this probability space of interesting lattices, and unlike in the previous case, now it is compact. But then, of course, there is also a price to pay, is that we don't have the analog of Siegel theorem anymore. We have lost that because now the space of our lattices now is too small, so they don't cover all space in uniform way. So, but then how do they cover our space? So here's maybe a mental picture and also a picture for those who are not mathematicians and for whom maybe previous slide was not that interesting. Okay, so let's look at our example. So this is an example, again, the same number field Q adjoint square root of 5. And so actually the class number of this field is 2, but here I took only one lattice for the presentation purposes, for the principal ideal. So this is again the embedding of our ring of integers. And so now what I do to my lattice, I take any real number t, and I multiply one of the coordinates with t, and another coordinate with minus t. And this way, I deform my lattices. And so what will happen that my lattices, they will still, if I multiply this lattice with any element of the group of units, it will still be its symmetry. So this way, the lattices are changing, and this group of symmetry we wanted to have, it's still preserved. And so this is how it looks like. So here I'm choosing like different numbers t. And so here you kind of see how compactness kicks in. So now if I somehow, we will see that in this multiplication by t, there is a certain periodicity. Actually, because when my t becomes equal to the one of the elements in the group of units, then just the lattices are preserved. And so actually this Arakelov class group for this number field, it would be a union of two circles. So this would be like this one-dimensional story. But you also, from this picture, you can also see how our lattices, how they cover the whole Euclidean space. So they don't equidistribute everywhere, but they concentrate in this case on the hyperbolas. So these are all the possible, the norm of number here would be all the possible norms in my field. And then, of course, if we go to higher dimensions, these hyperbolas would be replaced by their higher dimensional analogs. And in a sense, of course, we have kind of lost the equidistribution, but at the same time, one can say that this is how we actually prove usually the Dirichlet theorem is that if we look from far away and maybe close our eyes a little bit, then it kind of still covers our space in a reasonably good way. And so this is what we are going to play with today. So this is a recent, so the result I would like to present today. So this is a discovery of my colleague and PhD student Nihar Gargava. So he found that I think everything I will tell you about later, it was somehow already known, and this is pretty standard, but maybe now the estimates for the convexity bounds became good enough so that we can actually squeeze out this result. And so what we have found, so if let K be a cyclotomic field, so this is, for example, the field I showed you before, it does not work. So this is a field where we take rationals and then we adjoin the roots of unity. And square 5 is not a root of unity, but somehow cyclotomic fields, they are not so photogenic. So that's why I did not choose them for my purposes. So let now K be a cyclotomic field. And so we again choose a ball, and we would like to, we consider this, our lattices, they will, yes, we consider our lattices in the Arakelov space, so they're uniformly distributed here with respect to the Haar measure, and we would like to see what would be the expected value for the number of lattice points in a ball for lattices in this space. And it turns out that here the answer has very similar form. So we again have 1, which is because every lattice has 0 point. And for non-zero points, we have V, which is the volume of the ball. But then Siegel formula does not hold. We also have an error term. And so it turns out that for cyclotomic fields, now we can prove that this error term will be actually small. And as degree of the field goes to infinity, it becomes kind of smaller and smaller and smaller. And we can control it. So this is, so here the estimate is written in terms of the invariance of the field of its discriminant. But now if we also insert what we know about the discriminant, then we would get an estimate like this. And so now let me tell you a little bit about the ideas which went into the proof. And maybe I can tell you that all the ideas somehow, most of them are not very new. They are rather classical. And yeah, one more thing I would like to say that somehow like what is one of the corollaries of this result is an improvement on the result of Venkatesh by a factor of 1/2. And on one hand, it's always nice to improve on something. On the other hand, since now, okay, we know that these random lattices, they are even much, much better. And also 1/2 is not such a spectacular improvement, but still. And so here the idea is more or less standard one, uses standard tools. So first step is to use the Heckes integration formula. So the Heckes integration formula, it allows us to somehow get this error term in such a way and relate the error term to a certain contour integral where the Dedekind zeta function of our number field is involved. And so then this formula, it actually gives us, and this form for the error term, it gives us, so now if we have some very good control for the Dedekind zeta function, then we could also say something nice about the error term. So this is the, so to say, a version of Siegel's mass formula only for our space with the correction term, and it works for any compactly supported function f. And then after a little bit of work, we can also obtain an analog of this for the indicator function of a ball. And here there are maybe some technical conditions that our number field should not be too small, so its dimension should be at least 8, which again means that all the examples that we could have, they are not very photogenic, would not fit on slides nicely. And so yeah, so here we have this like explicit form of an error term, and so now the last step is to estimate this error term. And so somehow here actually here we had like a lot of choice for the contour, but we have chosen it to be actually to have a real, the vertical line with a real part equal to the 1/2, because this is a critical line and it is well studied. There are many results that we can just use and import for our purposes. And so here's the recent result that I was talking about, which allowed us to get good estimates. And so this type of subconvexity bounds, they have long history with many forms, many aspects, a lot of improvements happening. So many people working in the area. And so here is one particularly nice recent result, which we can utilize, is this estimate for the L functions of Dirichlet character. And so this is also an explanation why we prove our result for cyclotomic fields, because the Dedekind function of cyclotomic fields, of course, it can be factorized as a product of such L functions. And so if we have good estimates for these L functions, then we also would have good estimates for the Dedekind zeta function of the cyclotomic number field. And so from this result, we can get this kind of control on the Dedekind zeta function. And so now with this result, we can actually prove prove this theorem. And so, yeah, and then what I would like to tell you at the conclusion is that, maybe the one thing to take away is that random ideal lattices for cyclotomic fields, they are as good as random lattices.